For decades, scientific modeling has followed the same rule. Humans define the equations, and computers run them. Fluid dynamics, climate models, protein folding, material science all rely on frameworks built by researchers, refined over years, sometimes decades. AI could accelerate calculations, optimize parameters, or classify results, but it could not invent the underlying laws or structures. That boundary just shifted. This week, OpenAI quietly introduced an experimental system capable of generating its own scientific models directly from data, without relying on human-crafted equations. Not approximations of existing theories, not faster solvers, but models that the AI constructs from scratch, optimized for accuracy, stability, and predictive value. It's an early step, but a profound one. If validated, this technology could transform how we understand physics, biology, chemistry, and complex systems in general. Instead of scientists designing the mathematical skeleton of a simulation, the AI learns the rules of the system by itself, then predicts behaviors humans didn't explicitly encode. It's the reversal of the traditional workflow. Humans observe reality and try to generalize it into equations. The AI observes data and builds its own internal rules. OpenAI describes it as data-driven emergent modeling. In practical terms, the AI is given raw sequences, motion patterns, molecular interactions, experimental outputs. It tests millions of possible internal representations. It evolves structures that match the observations with minimal error. And then it extrapolates how the system should behave under new conditions. The early results are surprising. In benchmark tests, the AI reproduced phenomena normally requiring hand-built physics engines. It identified hidden patterns in biological dynamics that standard models overlooked. And in some domains, it generated predictions that matched experiments more closely than existing theoretical frameworks. This does not mean the AI has discovered new laws of nature. It means the AI is capable of building functional rules that behave as if they were laws, without being told what the laws are. That alone is a paradigm shift. The system is not a replacement for physics or for human reasoning. It is a new tool, a model generator that can uncover structures humans might miss, compress complex systems into learnable patterns, and propose dynamics that researchers can then test and interpret. One of the motivations behind this project is the explosion of scientific data. Modern laboratories generate more information than theoretical teams can process. High-resolution microscopes, particle detectors, genomic arrays, atmospheric sensors, all produce data sets where patterns hide beneath layers of noise and complexity. Traditional models struggle in these environments. They require simplifications. They require assumptions about what matters and what doesn't. The AI bypasses those assumptions. It learns the system directly, without forcing it into a predefined equation. That flexibility is the breakthrough. But it also raises deeper questions. If an AI can construct a model that performs better than human theories, what does that mean for the scientific method? Does it reveal something about the limits of human intuition? Or does it simply reflect the advantage of raw pattern recognition at massive scale? OpenAI frames the technology carefully. According to their researchers, the system is not intended to replace scientific understanding. Instead, it is a proposal engine, a tool that suggests functional dynamics, which humans can then analyze, validate, or reject. It augments theory rather than overriding it. This mirrors a broader trend in research. AI is becoming not just a calculator, but a collaborator, generating hypotheses, proposing experiments, prioritizing patterns, and building structures we would not have tried ourselves. One of the most promising applications is in materials science. New compounds often behave unpredictably. Traditional simulations struggle with emergent properties. The AI can analyze large-scale atomic interaction datasets and propose functional models that capture behaviors without needing full quantum mechanical detail. Another application is climate submodeling. Weather and climate simulations rely on simplified approximations of clouds, atmospheric turbulence, and ocean microdynamics. Improving these approximations by even a small percentage can massively enhance predictive accuracy. OpenAI's system can learn these microdynamics directly from real data, constructing models that plug into larger simulations with higher fidelity. In biology, the implications are equally significant. Protein interactions, cell signaling, metabolic cascades. These are nonlinear systems with layers of feedback. Traditional models often break down when the complexity becomes overwhelming. An AI-generated model can compress thousands of interacting signals into a functional representation that predicts outcomes with fewer assumptions. None of this is magic. It is computation meeting complexity more directly than before. But the shift is not only technical, it signals a change in how scientific work will be organized. Researchers will increasingly focus on designing experiments that produce rich data sets. The AI will translate that data into functional models. Humans will interpret the structures the AI proposes, searching for meaning, coherence, and new theoretical insights. It becomes a cycle. Data informs AI models. AI models inform human theory. Human theory guides new experiments. And the loop tightens. This is not the end of traditional science. It is the expansion of it. Some experts compare this shift to the invention of numerical simulation in the 20th century. Before computers, many problems were unsolvable. After computers, scientists could explore parameter spaces far beyond manual calculation. This new AI-driven modeling could represent the next leap, allowing exploration of systems too complex for explicit equations, too chaotic for classical simplification, and too data-rich for human intuition alone. The risks, for now, are practical rather than philosophical. AI-generated models must be interpretable. They must be stable. They must behave consistently under new conditions. And they must not produce artifacts that appear accurate only because the training data was constrained. OpenAI emphasizes these safeguards. The system includes stability tests, counterfactual evaluations, and adversarial perturbations to ensure that the learned dynamics generalize correctly. The most striking aspect of the announcement is how quiet it was. No headline about breakthroughs, no dramatic language, just a technical report showing results that, if scaled, could reshape entire scientific fields. This is how many revolutions begin. Not loud, not declared, but through the introduction of a tool that shifts what is possible. In the coming years, AI-generated scientific models may help map exoplanet atmospheres, predict protein ligand interactions, optimize fusion reactor dynamics, or simulate ecosystems under environmental stress. The boundary between understanding and computation becomes more fluid. The work of interpreting these models will remain human, but the space of possible models becomes far larger than what humans could explore alone. OpenAI's new system is an early step, but it points toward a future where discovery is not just observed, but co-constructed by human reasoning and machine-derived rules working together. The scientific method expands, not replaced, extended. We are entering an era where AI does not just accelerate science, it participates in it quietly, efficiently, and sooner than expected. This transmission ends here. The next one is already forming. Stay aware and subscribe to Remain in the Signal.